Welcome to the season finale of Introduction to W-star Algebras. We're going to be proving proposition 4.64. Now, if H is a Hilbert space, and we have a net of positive operators, P sub alpha, on H that are monotone increasing and bounded by the identity operator, whereby saying that one operator is less than or equal to another, we mean that their difference is a positive operator itself. Now, it's very easy to check that this is a preorder. Now, if we have such a net, then there exists a positive operator, P, such that P is an upper bound for the net, and it's bounded by the identity operator, and the P sub alphas converge to P in the strong operator topology. So this is really an analog of what happens in the real numbers. Now, for the proof, first, we're going to notice that if we have a Q, a positive operator Q, that is bounded by the identity operator on the Hilbert space, then we'll have that Q squared is less than Q and also a positive operator. So this is because proposition 4.33 tells us that every positive operator has a square root operator, which is positive. So because we have that the identity operator minus Q is positive, there exists a square root of that operator, which is also positive. And since Q commutes with I minus Q, right, because of that simple calculus, then because of the last line in that proposition, we have that Q commutes with the square root of I minus Q. Now, consider this very simple calculation, right? So you have the inner product of Q minus Q squared applied at F with F. Then you factor that left entry in the following way. And now, since the square root of I minus Q is a positive operator, it's its own adjoint, so you can just pass it to the right entry. But then, because Q commutes with the square root of 1 minus Q, we can write this inner product in a really nice way, namely the inner product of Q applied at something with that something. And since Q is positive, then we have that is non-negative, and therefore Q squared is less than Q. So keep this fact in the back of your mind for a second while we examine this very simple consequence of having P alpha be less than P beta. And that is that since P beta minus P alpha is a positive operator, we have that by using linearity of the inner product, we get that the inner product of P beta F with F is greater than the inner product of P alpha F with F. Now, since the net of positive operators P alpha is monotone increasing by hypothesis, the following fact yields that this net of real non-negative numbers is monotone increasing, and it's bounded by the inner product of F with itself. This shouldn't really have the square brackets there, but it follows from the fact that P alpha is less than I for every alpha. So you just run a similar calculation to the one we did with P alpha and P beta. Now, because of properties of the real numbers, if you have a monotone increasing net, just like with sequences, it converges and therefore it's Cauchy. So this net is Cauchy for every F. So let's use that fact in the following calculation. Let alpha be less than or equal to beta. Then the norm of P beta minus P alpha applied to F squared is by definition of the norm induced by the inner product, the inner product of P beta minus P alpha at F with itself. Now, since P beta minus P alpha is positive, it's self-adjoint, so we can pass it to the left-hand entry and get the square of P beta minus P alpha. Now, since P beta minus P alpha is a positive operator bounded by the identity, we get that its square is less than itself because of what we had proven earlier. So, since that net of numbers is Cauchy, then this converges to 0, and therefore, this net of elements in the Hilbert space is also Cauchy in norm. So, defining Pf to be the limit of P alpha F, we have that since each P alpha is linear and the limit of nets is linear, that P is linear. Moreover, we notice that the norm of Pf is the limit of the norms of P alpha F, because the norm in a Hilbert space is continuous, and those are all bounded by the norm of F. And this just follows from a very simple calculation and the fact that each P alpha is less than I. Therefore, P is a bounded linear operator on H. Furthermore, since each P alpha is positive, which is equivalent to this fact, by taking limits on both sides, we get that by the continuity of the inner product in the first entry, that P is also positive. Moreover, by definition of P, the net P alpha converges to P in the strong operator topology. Now the last fact we need to show is that P is an upper bound for the net that's bounded by I. And this follows from another very simple calculation. So for the first non-trivial inequality, we're going to use the fact that the P alphas are monotone increasing. And then just by taking a limit on both sides, we get that P minus P alpha is a positive operator for every alpha. Now for the second non-trivial inequality, it's basically the same thing, right? You look at I minus P beta, and then you take a limit on both sides, and you get that I minus P is a positive operator. And this concludes the proof. Thanks for watching all the series. If you liked the videos, please smash that like button and make sure to subscribe for more quality content.